The constructions of ancient Rome have endured for thousands of years, while today the service life of buildings is no more than 200 years. We will tell you about the magical concrete of the Romans, incredible engineering solutions in construction, and at the end, you will learn about the secret ingredient that allowed their buildings to stand for millennia. Stay tuned until the end. It seems that everything in this world has its end, except for what was built by ancient Romans. Well, at least what hasn't been dismantled or destroyed after the fall of the empire or through wars. Consider, for instance, the Maison Carrée, a square house built in the center of the city of Nîmes in the early 1st century AD. The building has hardly deteriorated over time and underwent only cosmetic restoration when it was reconstructed in its original form in the 19th century, becoming a museum that still functions today. And then there's the Colosseum in Rome, of course. It didn't take long to build. The construction took about 9 years. It involved over 100,000 slaves that were brought to Rome from Judea for this purpose. The walls of the temple were constructed using stone or marble blocks of limestone, which were transported from Tivoli, a city located 24 kilometers northwest of Rome. Bricks and limestone were also used for the interior walls. The marble and stone blocks were connected with heavy iron clamps. If that's not enough for you, let's remember the Tower of Hercules in the city of La Coruña, which now belongs to Spain. This structure, located on a high cliff, was built in 117 AD. It is the only operating lighthouse from ancient times, and the interior still contains structures from the beginning of that millennium. There are dozens of such buildings, and the secret to their longevity lies solely in the engineering solutions that we will be discussing today. And first, we would like to start with its roads, because monumental constructions require delivery of construction materials. Thanks to roads, this was done much more conveniently and quickly. Like the buildings themselves, these roads were built so well that many of them are still suitable for use today. Initially, they dug a trench about a meter deep. Then, at the bottom of the trench, they laid white stone blocks, and the remaining space was filled with a thick layer of gravel. The top layer consisted of special plates with convexities to allow water to flow away. As is known, the engineers of the empire insisted on creating exclusively straight roads, which required enormous resources for clearing the terrain through which these roads passed. However, it significantly reduced their lengths and greatly increased their durability. But if roads don't amaze you, what will you say about the next Roman technology which clearly exceeded its time? The water-powered sawmill was a striking example of amazingly sophisticated construction technology developed in the Roman Empire. It consisted of a reciprocating saw driven by a water wheel. The sawmill could cut a large amount of wood or stone, saving a tremendous amount of effort. The water wheel was connected to a shaft linked to one or more saws, operated by a crank mechanism. The earliest known sawmill was the Hierapolis sawmill, built in 250–300 AD. It was the earliest known machine that used a crank with a connecting rod mechanism. The relief on the sarcophagus of Marcus Aurelius Ammianus, dated to 150–300 AD in the ancient city of Hierapolis, located near modern-day Pamukkale in Turkey, provides a clear representation of how it operated. Sawmills were widely used for cutting marble. A Roman poet named Ausonius wrote an epic poem about the Mosel River in Germany in the late 4th century AD and described the haunting sound of a water-driven sawmill used for cutting marble. This is how the famous Roman tiles were made, which were later used to cover buildings. But what do you need for any construction? That's right, water. Just like roads, the extraordinarily long aqueducts became a trademark and true engineering marvel in the life of the Romans. One of the limitations to the growth of ancient cities was the inability to reach water from any point within the city, and this problem was solved. Roman aqueducts were a complex system stretching over more than 400 kilometers, supplying the city with clean drinking and technical water. They allowed expansion not along rivers but towards landscapes that were more convenient for construction. Sometimes they constructed pressure aqueducts with steeper inclines. Most pipelines were hidden underground, following natural terrain obstacles. They often bypassed hills and mountains, or, less frequently, dug tunnels. Deep valleys with a drop of more than 50 meters were crossed by bridges, or the water was led through lead, ceramic, or stone pipes called siphons. But typically water conduits were concealed within the bridges themselves, just as they are done in the modern world. It's important to understand that working with ancient bricks or concrete required vast water resources, and aqueducts essentially freed up thousands of hands to engage in construction rather than water fetching. Now let's talk about the unique engineering solutions that the Romans were the first to implement in construction. The Romans were the first in history to create vast open interior spaces, thanks to their realization that arches could be rotated in 3 dimensions. To create a strong and reliable force capable of supporting such structures, a special substance was needed, and that substance became concrete, an achievement of the Romans, but we'll discuss that a bit later. Roman domes were used in baths, villas, palaces and tombs. They were usually semispherical in shape and partially or completely concealed from the outside, astonishing people upon entering the building. To support the horizontal thrusts of a large semispherical dome, supporting walls were extended beyond the base, at least to the dome's spring points. Sometimes domes were covered with a conical or polygonal roof. Various forms were also used, including saucer domes, segmental domes, and rib domes. The framework was made of wooden beams, which were then laid with special brickwork to evenly distribute the load. Concrete pouring was mainly used to decorate and smooth the angles, to give the dome its proper shape, or to hide them on the building's facade. Next, we have a solution that you certainly wouldn't expect to see in construction dating back a couple of thousand years. The Romans were the first to implement an idea still used in construction today: heated floors. The technology involved constructing hollow clay columns embedded beneath the floor's surface, solving several problems at once: fire and smoke hazards. At the time, fire was the primary source of heat, but buildings had a tendency to catch fire, and smoke posed a significant suffocation hazard. In the Roman underfloor heating system, the floor was raised, preventing the hot air from furnace from ever coming into contact with the room, channeling it into cavities below. A single furnace could serve multiple rooms thanks to an air distribution system. This was mainly used in Roman baths, where large areas needed to be heated without the risk of smoke poisoning people. Unfortunately, after the fall of the Roman Empire, the use of this construction technology disappeared from history for a long time. The monumental Roman sewers became one of the most iconic creations, even though they were originally built for a different purpose. The Cloaca Maxima, which literally means greatest sewer, was initially constructed to drain water from local swamps. Its total length reached 800 meters, and it still functions today, albeit as a storm drain. The scale of the construction is evident from the fact that in some places 2 carts could pass side by side through these sewers. The channel was 3 meters wide and 4 meters deep. Romans used not only gravity but also pumping stations to lift the liquid to higher elevations. Starting around 600 BC and over the following centuries, numerous aqueducts were added. It's challenging to pinpoint when this system evolved into a full-fledged sewer system, but as cities grew, sewage systems penetrated deeper, eventually covering them entirely. Although the invention of the arch did not belong to the Romans, they found a way to perfect it. Roman engineers realized that to give a structure strength, an arch didn't have to be a single piece. It could be divided into multiple smaller segments. This allowed them to create much more robust and reliable bridges that could span several sections. The Limera Bridge in southwest Turkey, measuring 330 meters in length, boasts 26 segmental arches with a slight rise, giving the bridge an incredibly flat profile that remained unrivaled for an entire millennium. Trajan's bridge over Danube had wooden segmental arches with open spans supported by 40-meter concrete piers. It became the longest arch bridge in history for the next 1,000 years, both in overall length and the length of the individual spans. The longest surviving bridge is the Roman bridge at Merida, measuring 790 meters. However, constructing such objects without specialized equipment was nearly impossible, and the Romans managed to create unique devices for this, which we'll talk about next. As we mentioned earlier, during the peak of the Roman Empire, stone processing became significantly more sophisticated. In addition to chisels, picks, mallets, and mauls used for rough hewing, the Romans widely employed the tooth chisel and a complete system of saws, hammers, and chisels for finer carving. They also used not just drills but also a bore, which appeared during the Hellenistic era. Stone was cut using various types of saws, shaping it into the required form for construction, resulting in a relatively reliable brick that had to be lifted alongside heavier blocks. This is where the following tools came into play. The lifting mechanism, called a trispastos, consisted of two wooden beams joined at their place of connection by blocks, one stationary upper block and one movable lower block, along with stongs for gripping stones. The rope passing through the third lower block wound around a winch turned by levers. As the rope wound up, it lifted the weight, and as it unwound from the winch, it lowered it to the intended location. A polyspast was a similar lifting device but with 5 blocks. This complex engineering device was built on a combination of block systems, a winch and a lever. The driving mechanism and transmission mechanism of the trispastos were combined with the executive mechanism in the form of simple tongs or hooks. To lift heavy loads, the driving mechanism was supplemented with a wooden stepping wheel, which was turned by slaves walking inside the wheel. The most advanced trispastos and polyspas systems were apparently placed on a round wooden platform that rotated around a vertical wooden axis, similar to modern lifting cranes. By the way, it's essential to clarify how the construction process was organized, as the work planning was very progressive and somewhat resembled modern practices. While the details of construction techniques reflect their penchant for efficiency, the overarching organizational genius shines through their work distribution. The methodical allocation of responsibilities had not yet reached such a level. For each type of work, there was a specialized guild of workers with specific qualifications and traditions. A close examination of major architectural monuments confirms the systematic division of labor among these shifts of workers, each with its distinct specialized role. The system is especially evident in the decoration of building facades. There are very few structures such as the Pantheon, where columns were installed simultaneously with the construction of the walls. Typically, decorative elements were prepared during wall construction and were installed later, providing a significant advantage in terms of construction speed. The Romans first constructed the building, and then marble was attached to the walls using clamps, or they were covered with a layer of plaster. This method was inevitable in architecture where the structure's mass could not be artistically treated, but it had lamentable consequences from an artistic perspective. The Romans' habit of considering building and finishing as entirely separate factors inevitably led them to view these factors as wholly independent of each other. Over time, the finishing became more arbitrary, and the buildings in the later years of the Roman Empire became more standardized and dull compared to those of the empire's early days. Now let's talk about the most crucial invention that revolutionized construction technologies of that time. In our time, concrete is widely used in construction projects of all scales. Ancient concrete consisted of a mixture of volcanic ash, gravel, lime, and sand. Concrete allowed them to cast shapes of any form and was incredibly sturdy. Initially, Roman architects used it for casting the bases of altars. However, in later times, various experiments were conducted with this material, resulting in wonders like the Pantheon, the world's largest non-reinforced concrete structure that is over 2,000 years old. Scientists have discovered that the longevity of Roman concrete was not only due to the volcanic ash they consistently added during construction. Through careful examination of several samples, researchers found that the ancient concrete production techniques included what specialists call key self-healing functions. By this term, they mean tiny, bright white mineral fragments known as lime clasts. In simple terms, small pieces of unslaked lime, which were abundant in Roman concrete specimens. Subsequent tests showed that this type of concrete, when exposed to water, didn't deteriorate. Instead, it absorbed some of the moisture, strengthening the overall structure. According to scientists, unslaked lime was intentionally created as an additional ingredient in concrete and was not a sign of low-quality control during the mix's production. Romans maintained an incredibly strict discipline and adhered meticulously to developed technologies. In a society with forced labor and militarization, there was no room for cutting corners, especially in the construction of each building. The Roman Empire employed incredible construction technologies that remain relevant to this day. Thanks to stringent quality control and adherence to these technologies, their buildings have stood for millennia. There's much we can learn from this. Thank you for watching.